So first of all, any last minute questions about the exam for Friday? Anything you want me to cover before we move on to new stuff?
What are the answers?
Well, I don't know what the questions are yet. so
Did you answer Maddie's question?
I answered it right away on. Would you like me to answer it again in here?
No, my phone's been.
No.
He said it is because HTTP has been around for a long time and has been tested, and most APIs can be implemented in terms of fraud.
We talked about CRUD in class. Then I even emphasize what it means in there.
No, I'm just saying fraud. Like, I was about to say crude.
Oh. So you stop reading now? You were reading for the class.
So
And then
HTTP is kind of built for those 4 functions. And the 4 functions are free up to
I would have probably done it in a lower voice, but I guess to each their own. All right. So let me bring up the. If you haven't already done so, first of all, everybody's going to be at the CS Get Together tomorrow at what time does it start? 11:30. So make sure you're there maybe a couple minutes early because that's when we hand out the sheets for the meet and greet, Dealy Flippy. I know that's an anxious time. You don't want to really socialize with other people and stuff, but it's also the opportunity to get the best prizes. So that's tomorrow. If you haven't already done so, make sure you, I'll just use the slide from this. Make sure you email Professor Josh Locklear about the hackathon April 14th. Let him know whether you want to do VR or mobile app stuff so we get you onto appropriate teams. Yeah, so remember that's required for all of my classes. Not for senior SEM though, although for senior SEM I would strongly encourage you to go to it because you should. But I can't really add another assignment into that class, so I likely penalize you in some other way to be, I don't know, dished out later, maybe, I don't even know. It's an empty threat somewhere. It's What's up?
What was the topic for the paper review stuff?
What for the
like if we didn't do it?
Oh, I don't know. I haven't come up with that yet either, but it'll be bad.
Well,
Like it'll be a very dry topic and a very long paper.
it sucked last year.
You told me you're not. Well, you said you would start that game.
I would play, because we're playing Concord Chicago.
No, it'll still probably be bad.
Should be like the evolution of mobile applications.
Probably way worse than that. Like it'd be more like, where do baby chickens come from?
Oh,
Write a 27-page paper.
Actually, you want to read that much detail.
That's how you get nonsense.
Hey, you gotta throw filler in there.
Just take a tangent.
What's up?
Just take a tangent. Like start talking about like incubators and everything.
Manufacturers and the ideal temperature if you're south of the Mason-Dixon line.
There's actually like a lot you can write about that, because there's like the whole conversation of like if those farms are ethical or not, because like all those chickens that like we even like.
Oh, so you like the idea is what you're saying?
Yeah.
What is to be a biology major you're talking to? I mean, come on.
There's like entire movies about it.
Did you see the? I know this isn't necessarily related, but it's equally interesting. I think stuff. Did you see this? Some YouTube guy. I think he's from a different country, but I'm not sure. But he has been arrested for a hate crime for training. I think it's his girlfriend's pug
Yeah.
to do like Nazi stuff.
So it wasn't even like training him. He just put him in Nazi scenarios.
he
He
just
just made
made
him
him
watch
go.
like a Nazi video. And
Yeah, but he was like saying keywords, and then the dog would always respond to that and not to anything else.
yeah, like gas.
Yeah. So it was. I don't know. It's.
I mean, he was like, I'm gonna turn it into the worst thing imaginable.
Yeah, no, I get it. It's just, I don't know. I honestly don't know. Like, there are some things mean, you have the freedom of speech stuff, and then there's like some things you just really shouldn't joke about. And I just don't know where that falls.
I mean, it was
It's
a
not
dumb
hate
thing to
speech,
joke about, but I don't think he should go to jail for it. Yeah.
Well, I think it didn't help that he also on his YouTube channel had a lot of other kind of more neo-Nazi type.
I gotcha. So it wasn't just this;
So
it was.
wasn't just one video.
I gotcha.
Like
Yeah.
jail time though. Seems a little
Well, I don't know.
He can get up to like a year, I think.
I mean, my guess is they won't give him that level
Well,
of.
they want to give him 5 years. Yeah.
Yeah, I don't know. I mean, it'd be.
He's in prison?
Yeah.
Oh my gosh.
At this point, he's probably ruined.
Hey, I mean, the dog really consistently replied.
Dog. We're not talking about another human.
Hey, look, that was a smart dog. I'm just saying. He, like, with 100% consistency, replied. And, I mean, I'm going to call it 100% effort every single time the dog was asked to make a gesture. The dog tried his hardest to do it. I mean, it was uncanny, really.
Is YouTube that guy's profession? Because if it isn't, it's not like he hasn't already ruined his life.
Yeah, I don't know.
Because he's not going to get a job now.
I mean,
I don't know if that's true, but yeah, I just found it interesting. I saw that on the news this morning, but doesn't that fall into the category as for all of us? Like, be careful what you post on Facebook and stuff like that.
Hashtag
You know.
delete Facebook.
Oh, that's the WhatsApp guy, right?
No,
That's everybody thing right now.
it's
But
that thing that the politicians hire, that company that politicians hire, they've been using like what is it called?
Oh yeah.
Muat, you're here. What's up? I haven't seen you like in a month and a half. Well, spring break was only last week. All right. So, all right. We're talking about interprocess communication stuff today, right?
Sure.
Okay. So we were talking about our chat server stuff last time, just at the high level. Now we got to start thinking about how can we make multiple processes talk to each other. So today I'm going to kind of introduce this. We're going to take a little baby step in. I'm going to look at it. We're going to look at two different examples. I hope these will end up working on with little or no modification on Cloud 9, but I guess we will find out. But at the very least, I have them working locally on my machine, so we'll walk through the code and we'll understand how those things work. All right, so while this guy is doing his thing, we were talking here. We mentioned this idea of shared memory last time, where we have, and think of this almost like our singleton model. So that idea where it's a good thing when you have more than one object was the way we've always thought about it, to store all that information in one central place. Well, the same thing's true here. If we can create memory in the computer's architecture that is accessible by multiple processes, we can all check in with that place to share information. Okay? So now we have to have a mechanism for creating that shared memory, because what we've seen in the past is when we do, let's kind of draw a little picture of this. So let's say we have a char pointer AR, and this guy's equal to some malloc thingy. So that's shorthand for malloc thingy. All right, and this is one process. And we do a fork. What happens is we get a duplicate of this process, and we'll just say next line here. Next line here. So once we do a fork, maybe this is the original and this is the new child. So fork will return a process ID of 0 for the child and the process ID of the actual child to the parent. Then we go on to the next line. So both these guys is usually going to be some if statement, right? If I'm the parent, do this. If I'm the child, do this. Now, under our normal circumstances, when we think of malloc, we think that we're allocating brand new memory, right? But the issue here is that when we create a copy of this process and we get this guy, those two copies have different memory footprints. And let's actually look at this. We'll do this through, the following components will be installed. Oh, okay. Just exciting stuff. Can I click back here while it's doing it? Oh, guess not. Big money. Well, here, I'll start writing my code over here on another.
It only takes like a minute.
That's fine. I'm going to write it anyways, so this isn't going to hurt anything. Here, I'm going to steal. I'll just steal all this crap, and I'll remove what I don't need. Or I'll just keep it in there and not use some of it. All right, this is going to be fork test .c. Okay, so we'll have int main int argc char pointer arg v. All right, so we got that guy. So what we'll go ahead and do is we'll create a char pointer AR. This guy is going to be equal to whatever malloc returns for, I don't know, let's just do 100 times size of char, which is 1, right? So we'll just leave it at 100. And that's going to give us some memory. So I'll go ahead and do a printf. How do I get the memory address of that dude? Guess I can do %p. And we'll print out AR. Just make sure this part works first. It's funny. I literally just copied a whole bunch of stuff, but never actually gave myself enough to include malloc. Because we don't need malloc with shared memory. All right, memory addressy looking thing. Fair enough. That's what I wanted. Okay, so I'll go ahead and create this shared memory, or not shared memory. I'm just creating some memory. Nothing new, right? Malloc, some memory. And we'll print out that memory address here. Then I'll go ahead and say int PID is equal to fork. So we will split this into two processes that are copies of each other. All right. Then what I'm going to go ahead and actually with shared user space on Mac, I hope this works the way I want it to work. Suppose we will find out. I'll go ahead and have each one print these again. In fact, we'll go ahead and say if I'm the child or not. So we'll say if PID is equal to 0, then we'll say child that else parent that, and that was weird. Oh, I guess it was my own fault. All right. So we're going to create the memory initially, print out the address of it. That's only going to happen once. Okay? In fact, we could even say original. All right. Then we'll split. Well, we'll create a child process. If I'm the child, I'll print out the address of my AR. If I'm the parent, I'll print out the address of my AR. Or his AR, something like that. Oh, it did do protected. That's not what I wanted to do. All right, let me try something here. make sure this does what I want it to do before I... Okay. It's going to be crummy to explain, but at least this proves it. See, the issue here is that in more modern Unix operating systems, you have process-based protected memory. So up here, you saw that the memory address for all these guys was actually the same, correct? I mean, these are all the same memory address. So we would presume that any changes we make to that global memory location would be felt everywhere. But this actually is not a global memory location. It's a memory location that exists as kind of a local memory spot within the PCB. So even though they look like they have the same address, this is kind of like a local address, almost like a non-routable IP address, something like that. So we can see down here that here's our original memory location, and we've seen that it stays the same for everybody. When we get to the child prints out their version of that, so we get the hello. The child then changes it to goodbye, prints out goodbye. Okay? Now, the parent waits a second. I put a sleep thing to wait a second to let the child finish all of its stuff. Then the parent reads from that same memory location, but gets the original, which is hello. So the parent did not notice the update from the child. Make sense? All right, so we're going to call this the weakness of not being able to use, if we don't use shared memory, this is a weakness because we don't have a way of crossing the PCBs. That makes sense? Historically, what we would have actually seen here, at least I'm pretty sure my memory is not failing me, certainly the behavior supports this. We would have seen actually these two addresses would have been the same, but this guy would have been different. The parent would have gotten a duplicate of the PCB, and all memory things in there would have been copied. New memory would have been created for them with a new memory location. Does that make sense? Certainly the behavior supports that. So that's at least how it's behaving anyways, regardless of the underlying memory addresses. So in this model here, we aren't able to have the parent and the child talk to each other through that shared memory location because at the very least they're acting like they're different addresses. They're local copies of each other. All right, does that make sense? So we need some other way to get these guys talking to each other, at least as a starting point, even if they're just sharing a single secret message between each other. In this case, I'm doing the hello, goodbye with a little bit of a pause thing in there. So if you're the child prints out, this is what's currently in AR, which is hello. Then the child changes it to goodbye. Then the child prints out the proof that it's changed. The parent printed it out initially, which was right here. That's the hello. So here's the parent and the child. These guys are happening kind of at the same time. Then the child changes it, but the parent sleeps here. So if I do let's do a printf, waking up. All right, so notice that the child has already written the goodbye to this guy before the parent wakes up. I had the parent go to sleep for a second, so we had some time well, we assumed that the computer would be able to get all that crap done in the 1 second, but it did, right? All right, so we see that the parent did not realize the changes that the child made, so it must be happening in different physical memory locations. Okay, so look the same, but we're not able to talk. All right, and this is more of a modern protected memory type thing where you have one PCB that can't crash another PCB, or can't is probably the wrong word. It would be unlikely for one process to crash another process. It would have to do so by means of corrupting the operating system. All right, historically, it was easier to accomplish something like this, but we would have seen the same behavior here, where they would have just actually had different memory addresses. So we would have gotten the same output had we written this program 20 years ago. We would have seen the same output here. We just would have seen slightly different output here because these two would have been actually different memory addresses. Okay? So we need a fix. We need a way of getting around this. And let me, this guy done. While we're at it, let's just test my little sample thing here real quick on Cloud9, make sure Cloud9 behaves the same. I think it will, because this is a newer operating system type thingy. So, all right, so we have the same output there. It's the original. Just for the sake of testing, let me just throw the memory addresses out here real quick. I think they'll be the same. I'm just curious. Yeah, they were all the same. So acted the same across the two of them. Okay, so now I'm going to look at two different approaches to this. We talked briefly about IPC last time, this idea of inter-process communication. Why would Bixby open up when I say IPC? It's personal assistants. They're just kind of all they're cracked up to be. What was I saying? Oh, okay. So inter-process communication. This is going to be a set of tools provided by the operating system for processes to talk to each other. Because at the end of the day, the operating system itself is our mechanism. I mean, within this operating system was where all our processes live. So if we can't get these guys talking to each other directly, we have to use the operating system itself as a kind of a bypass. All right. So we have two different examples. So we're going to look at kind of what did we do before there was a kind of a built-in tool for doing this. So what was the hack? And then this is probably how shared memory is actually implemented behind the hood. All right, so I'm doing a pretty similar example here. So I have a little function called create shared memory that just returns a void pointer. So we don't care what kind of memory it is. It's just a chunk of memory that's going to be shared between these two things. So we'll create some shared memory. And we have some things in here for protections. And this allows us to see some bitwise shift stuff. I think I mentioned this a couple of classes ago. So the protection for this thing is going to be read and write. So we use a bitwise OR to kind of intermingle those things, mask them together, which gives us a resulting protection that gives us read and write. All right, so this is kind of the go-to move. When you have multiple features you want to give to something, they are masked together with bitwise ORs. Visibility, anonymous, and shared, we can look at what those are. I'm not sure what that necessarily means. I think you won't be able to see what process is writing and reading from it. And shared must mean the operating system can read it, but I am potentially making that up. Well, here, the buffer will be shared, meaning other processes can access it. Makes sense. Third-party processes cannot obtain an address for it. So only this process and its children will be able to use it. All right, fair enough. All right, so just permissions for our shared memory. And then what we're doing is we're using this tool called a memory map, mmap. All right, and this guy is going to, and let's actually, I'll come out here. I'll do man mmap. So this allocates memory or maps files or devices into memory. This sounds pretty similar to what malloc does, right? They do work a little bit differently, and we'll kind of go through this, but it kind of sounds like a competitor with malloc. One thing you will see is mmap is actually typically higher performance than malloc because it does less, it hits files less because of the way it's reserving memory. And notice this guy is a system call. I want to see what they how they advertise malloc. They advertise it as being part of the system or not. All right, it's possible I might be making an assumption here, but I don't think so. I feel relatively confident about what I'm about to say. Notice that malloc is not advertised as a system call. Okay, it's a function. It does some stuff. Okay, but ultimately it's doing that stuff within the PCB, and that seems to be consistent with what we've seen in the last several minutes. So it's reserving memory, but only within its own little world there related to the PCB. Where things that are system calls, these guys they're talking to the operating system. Okay, this is leaving the local house and going to the home office to, that is controlling everything. All right, but other than this, they're doing pretty similar things. They're creating some memory. It's kind of like who's in charge of creating the memory? Is it the local PCB? Or the guy who's in charge of the local PCB, or is at the global operating system level? So mmap takes in an address, takes in the length, how much how much memory we want to create, the protections, the flags are going to be the that other thing, the anonymous stuff, file descriptor, and then an offset. I think it'll tell us. So here's the protection: none, read, write, execute. And then here's these guys, anonymous. Tell us what those last parameters are. Maybe they're just optional. See how it's being used over here. All right, so we're calling mmap. We're saying we don't care where you start in memory. Find a place. All right, we're letting the operating system decide. Probably smart to always do that unless you have and this is actually something that happens in video games pretty often. If you've ever I've referenced this before. A lot of the tools for like cheating in video games look at specific memory locations because they know that's where certain things get written. There's a performance benefit to not have to talk to the operating system to request where a memory location is. So a lot of times when you're writing games, you make decisions that tend towards performance as opposed to, I don't know, intelligence. So if you're not talking to the operating system to find out the base address, you just know where the base address is, you're hard coding it, then you would give this guy a base address. And you'd be at, depending on what your permissions were, you may or may not automatically overwrite what else might be there. Right? But by saying null here, we're saying, go ahead and find me some memory. I don't care where it is, just give me some memory. Right? How much memory do we want? We want this much memory, which is the size that is passed into our create shared memory function. Now, this is a variable of type size underscore t. Naming conventions like this almost always means that this guy is a struct. That's the type of value that guy is a struct. This is more just a naming convention. Just like in Java, objects typically start with a capital letter. Structs usually use this little underscore deal in there with a T at the end of it. All right, so we want the size. Here's our protection and visibility values, and then 0, 0 for those last two. What were they even called in here? This is the file descriptor and the offset. My guess is this is if you're mapping memory related to a file. You might use those last two, but I have probably used it before, but I don't remember it. All right, so we're just throwing 0 and 0 in there because we're not using those pieces. And we're returning the result of mmap, which should be a pointer to a place in memory. All right, and this guy's returning a void pointer because it's not built for any specific sort of type. It's just, here's a plot of land. Put what you want here. Okay, and this is where it is in memory. Does that make sense? So that's what mmap is doing, but it's a system call, so it's relying on the operating system to do the heavy lifting, to create that memory. All right, so now back in main. So I prototyped this guy, but just writing it up here. I was slapping this together today. So I have a couple of string literals. Hello, goodbye, same kind of crap we were just doing a few minutes ago in our little test thing. Then we're going to go ahead and we're going to get our void pointers that's going to point to our place in shared memory. What we're calling shared memory. We're not actually using interprocess communication stuff built into the operating system yet. We're kind of doing the old school way of doing this of, hey, I need to have memory share between two processes and I want to move outside of the PCB local memory restrictions. All right, so that's what we just used this create shared memory thing, which ultimately just did an mmap. Okay, so this guy here is going to be a pointer to that place in global memory. All right, then we went ahead and we did a mem copy, which is, from our perspective here, is going to be very similar to a string copy, strcpy, which will copy the parent message, which is this guy, into our shared memory pointer, so into this place in memory, and the size of this guy, which I think currently gives warnings, because size of for a string literal was giving me weird stuff. This is correct, but it gives a warning. There's probably a way to get around it. But in any case, we're copying hello into the shared memory location. All right, then we're doing our fork. So now we're two processes. All right, if we're the child, so if process ID is 0, we'll go ahead and print out so the child is going to read the string that lives in shared memory. So we'll read that out. It's going to read in hello. Okay, and we'll print it, child read hello. Then the child's going to change. So we're going to mem copy into shared memory. You could also use string copy here. It's the same thing. All right, for what we're writing strings. Mem copy would be more generic. Copy this memory into this memory. I don't care what it is, just copy it. Okay. So we're going to copy into our shared memory location whatever child message is, which is goodbye, and then how long it is. String copy gives you the advantage of you don't have to tell it how long it is. So since we know we're dealing with strings here, string copy would probably be the more convenient. Certainly we get rid of my couple warnings. But I kind of was copying from places and just meshing something together for our example. So I have two examples here. All right, so we have our where child's reading and printing it out, then child's changing it. That's what we're doing here. And then the child's printing it out again, proving it changed it, just like we did a few minutes ago. Now, if we're the parent, this guy, we'll go ahead and prove that we had the same original. So it should say hello, just like we had before, because we're both kind of reading immediately. We are at the mercy of the operating system as to who gets CPU time next, the parent or the child. Chances are it'll be the parent, unless we just happen to be out of CPU time immediately following the fork. Chances are the parent will have a couple more instructions on the CPU before they get kicked off. So more often than not, the parent is probably going to print out what they read first, I would suspect. But it might even show up in the screen out of order, because now when they actually print something, you're going into the I/O queue, and depending on how that's processed, things might come out in a different order. But in any case, we should see the child and the parent, what they read should always be hello before any changes have been made. All right. Now, the child is changing it, which should be, let's call it relatively instantaneous, while the parent's going to go to sleep for a second. And we're presuming a second is long enough. Today's computing speeds, a second should be plenty long. If you're on a really old computer and you're doing more than just copying something, you might need to make it more than a second. And so you should already be seeing that this adds a little bit of, maybe shared memory isn't all it's cracked up to be. Maybe we need something else to kind of go with that guy, if we're just kind of rolling the dice as to whether the changes have been made or not when we read it. So we'll have to think about solutions for that. There are solutions, but before we look at real solutions like semaphores, we're going to look at our own internal, like, how can we hack this? How can we make this work with the tools that we have provided in front of us? So a parent will go to sleep for a second. Presumably the child's made their changes in that second. Parent wakes up. After 1 second, the parent reads from it and should see the goodbye. In effect, receiving a message from the child. Two separate processes. Child changes this global memory, parent reads from that same global memory. So now we've left the local memory space of the PCB and moved to a global memory space of the operating system. Make sense? So that's what should happen. And this is shared memory example. It's my first one. All right, so there's my couple of warnings about the size of the parent message. If this gives me the correct response, what it's giving now. So I have no errors, just 2 warnings. So this operates on objects of type char while the size is a char pointer. But if you put in the value here, it'll like give you the first letter. So just roll with this for right now. All right, so parent read hello, child read hello. Now parent's going to sleep, right? Child changed it to goodbye, shows it as goodbye. After a second, parent read from that same global memory and sees the change, which is goodbye. See how that behavior is different than our behavior up here, where our logic is the same, effectively, right? So that shows that we have now left PCB local memory space. PCB is probably, I keep saying it, it's probably not accurate. Local memory space is probably the better way of saying it because I'm not sure how it's actually implemented in modern Linux. I probably should look into that at some point. But side effect is the same. So we're consistently understanding what the result is. Okay, so this shows a shared memory-like situation, correct? Questions about that? All right, so now we have a bucket, a singleton, if you will, that we can use across multiple processes. Let's go look at, let's look at my other example first, and then we'll copy both of these into Cloud9 and make sure they work there. So that is using, let's call it pre-standardized interprocess communication stuff. Now we're going to look at my shared memory example 2. And notice this guy brings in an IPC.h file, which is part of the system. So interprocess communication is part of our modern operating systems. And notice we have this thing called a shared memory key. This can be anything we want it to be, so just pick your favorite number. But it needs to be a number that somebody else isn't using. Because this is like the unique identifier on the system for 2 guys to find the same place in memory. All right. So here's my couple of string literals, hello and goodbye, same as before. All right, so now I'm setting my shared memory ID. So this is a global variable for this program. This is going to be an integer, so this is kind of a pointer, like a file descriptor like we had before. And we're going to say shared memory get. So we're going to get some shared memory, given this key, given this size, and the option we're creating new shared memory. Okay? So that should do the magic, associate some shared memory with this key, and then ultimately store it inside this idea, this ID. All right. So now we're going to go ahead and get a pointer to that place in shared memory. So we have this location in shared memory up here that just exists. All right. So now what we need to do is we need to attach to that shared memory. So we're going to go ahead and attach to this place. That's our file descriptor. All right, and I just want to make sure I advertise this to you correctly. We don't need to tell it the address because it'll be receiving the address. What are the flags? All right, flags have to do with how you round addresses, offsets on addresses. So if we look at what it's doing right now, I want to get this guy. No, I'm sorry. I want to attach to the shared memory given this ID. We don't care where the base address is, just like we had before. And we don't need an offset because the shared memory ID is going to tell us exactly where we need to go. This would be more like giving it the full address to where it is in memory, where the shared memory ID isn't necessarily being used. So in this case, you would probably have a null here and then give it the actual pointer in here with a potential offset. But in any case, we're attaching to our shared memory. And this is going to give us in this case, a char pointer, because that's what we're asking for. All right. Then we're going to do our mem copy, or we can do string copy just like we did before. Just like I mentioned we could have done before. So we're mem copying our parent message into that place in shared memory. We're going to do our split here. Child reads from shared memory. Child changes shared memory. Child proves they've changed it. Parent reads from shared memory, sleeps for a second, writes to reads again, noticing the child's change. In the end, both the parent and the child have to detach from that shared memory. All right, so the same stuff that was happening before is happening here. We're just doing it in a more compartmentalized way where we didn't have to write this extra little function, this create shared memory thing. The presumption is whatever is inside of IPC.h has written something along those lines that generates some shared memory, attaches to that shared memory, detaches from that shared memory. So there's some functions that already exist, and I'm not necessarily sure exactly how the shared memory get and the shared memory attach are implemented. Presumably they're implemented a little bit differently than this, but they very well might be implemented in terms of mmap. I mean, certainly the behavior indicates that that's a reasonable way of implementing it. All right, so if I come out here, now I will show you this. I'm going to go ahead and run this. Okay, I get the same warnings I had before. They'll go away if you do a string copy. And then I'll do a.out, and we get a segmentation fault. This is kind of an interesting thing that gives us a little insight into what's happening under the hood. So I'm going to do sudo./a.out. I'll put in my password here, and notice it works. It works now. So the shared memory system as we're using it here, and there might be a flag that we can change, but my guess is it might not operate like this on Cloud9. We'll test it over there here just in a second. In fact, I'll start copying it now since we're almost out of time. But Macintosh has their operating system pretty locked down. They won't let you directly use the interprocess communication shared memory version unless you operate as super user. That's what sudo does. It says run this as super user. So just real quick, let me copy my version 2 of this guy. And I will paste that into my fork test just for convenience. Save. Yeah, I get the same. So, very interesting how the built-in shared memory requires super user access in order to directly manipulate it. I'll look into if there's a way around that, but while still using shared memory. But if you get a segmentation fault, you need to run it as a super user. So I'll look into that, and I'll give you the punchline next time we meet to talk about stuff. But on Friday, we have our midterm. I will get them graded definitely over the weekend, hopefully actually on Friday, because I think I have to have midterm grades turned in on either Monday or Tuesday, but something like that. All right, questions, comments, concerns, bribes? All right, I will see everybody on Friday.